This is part 3 of our video series for limits at infinity. And so now that we've talked about limits with the radical, I wanted to do this example, which is find the limit as x approaches infinity, so just positive infinity. So I'm going to write it as the limit as x goes to positive infinity, right? It didn't specify negative infinity of this function. So I have the square root of x squared plus x plus 1. Notice that this x is outside of the radical, so minus x. I'm gonna want to make sure that when I write it, that it is clear that that x is outside of the radical. All right, so as x goes to infinity, what is happening here? So technically, you have as x goes to infinity, infinity square, right? Not really infinity square, but a large number. Square is going to continue to be large. So think 10 million square. It's really huge, plus 10 million plus 1. At that point, that plus 1 is pretty irrelevant, right? So it's the variable is really what's making this blow up. So it looks like you're going to have an infinity minus, and then as x goes to infinity is infinity. The thing to be careful here is that this isn't, so my little warning here, this is not necessarily 0. So it could be, but it doesn't have to be. Infinity is not a number, right? Infinity is a concept indicating that numbers are going on forever. They're getting arbitrarily large. So how large? This infinity could be larger than this infinity or the other way around, right? So we just know that we have large numbers here, but we don't know that they're the same magnitude. So how do we do this then? I have infinity minus infinity. That's not doable. So here, because I don't have a rational expression, we are going to use our trick of multiplying by the conjugate when we have radicals. So notice that I don't have anything in the denominator, so I'm going to put a 1 there so that it looks like a fraction. So when I multiply numerator and denominator by the conjugate, it looks like I have a denominator. And try to make it very clear that that other term, that plus x, is not inside the radical. So you'll see me do this little box at the end of the radical just to indicate that the radical ends there. Sometimes people put it under parentheses, and so that's fine too. All right, so now let's do our multiplication. So this is the limit as x goes to infinity of, what do I get? Square root of this times itself. The square root cancels, so I'm just going to have x squared plus x plus 1, and then minus x times a positive x, I'm just going to get minus x. It's just a one term here, minus x squared, so I don't need to put parentheses. If I had more, so if this were flipped, I would have put parentheses behind the negative here. Divided by 1 times that conjugate. So I'm just going to have that quantity plus that x outside the radical. Combine like terms, try to simplify as much as you can. So I have the limit as x goes to infinity of my x squares cancel. So I'm just left with x plus 1 over the square root of x squared plus x plus 1 plus x. And now I have this, now I have a rational expression. And so now I have infinity over, now I have infinity plus infinity, right? And so this, I can't do anything with that. So here we're going to use our tools from the prior video. So I'm going to identify the highest power that appears in the denominator. So x there, and notice here I have the square root of x squared. And just as we talked in part 2 of this series, the square root of x squared is the absolute value of x. And so we need to define it. So as x, if x is greater than or equal to 0, or negative x, if x is less than 0. Luckily here, I'm just going as x goes to infinity. So the square root of x squared is going to be just positive x. If I was taking the limit as x went to negative infinity, then this term will become negative x. All right, so let's keep going. So I'm going to divide everything by x. So I'm going to have the limit as x goes to infinity, dividing every term by x. This is part 3 of a video series, so I'm going to skip the division part. So I'm just going to say x divided by x is 1, plus 1 divided by x is 1 over x. And then here, right, this is going to be my x squared divided by x, so by x, the square root of x squared. So I'm going to have the square root of 1 plus, inside the radical, right, dividing by x means I divide by x squared. So plus x over x squared is 1 over x plus 1 over x squared. And then I have plus x divided by x itself is 1. And so now we take our limit as x goes to infinity. Anything that has an x on the bottom is going to go to 0. And so what are we left with? We're left with 1 over the square root of 1 plus 1. So 1 over 2. So remember, we started with infinity minus infinity. So my warning here was that infinity minus infinity is not necessarily 0. So this is my warning. Okay. And in this case, notice that for this limit, infinity minus infinity is 1/2. So I can say, therefore, oops, I don't want red in there. Therefore, the limit as x goes to positive infinity of the square root of x squared plus x plus 1 minus x is 1/2. So that means that this function has a horizontal asymptote at y equals 1/2. So y equals 1/2 is a horizontal asymptote as x goes to positive infinity. It will be interesting to know what happens as x goes to negative infinity. But we probably actually can't go to negative infinity because it's not in the domain of the function. Right? We're taking the square root of stuff. So, all right. So let's go on to the other examples. So for this next examples, we're going to focus on vertical asymptotes. We've been talking a lot about horizontal asymptotes, but what happens when you have vertical asymptotes? So let's look at the limit as x goes to 0 of 1 over x squared. So when do you get vertical asymptotes? So vertical asymptotes come from when the denominator is 0, or when the function is undefined, usually when the denominator is 0 in a rational function. And what that means is that when you take the limit, so if you have the limit as x goes to a of a function, say like p of x over q of x, and p of a is some number, so it's defined and not equal to 0, and q of a is 0. So that's when you're going to have then a vertical asymptote. So q of a is 0, but you have a number on the top. So what that means is you're going to have a number over 0. So that likely means you have a vertical asymptote at x equals a. Right? Notice now, horizontal asymptotes are y equals, because they are horizontal lines, and vertical asymptotes are x equals, because there are x values, and they come from, usually from a denominator being 0. So here, for the first one, find the limit as x goes to 0 of 1 over x squared. So notice that if you plug it in, right, if you plug in 0, you're going to have 1 over 0. So that fits the characteristics of a number over 0. So we're likely going to have a vertical asymptote here. So whenever that happens, so when you plug in the value and you get a number over 0, what we're going to do is we're going to look at one-sided limits. So that means you're going to look at the limit as x goes to a from the right of your function and the limit as x goes to a from the left of your function. So let me copy that function again. So I have my limit as x goes to 0, 1 over x. With limits, first thing you do is plug in, so you get 1 over 0. So this means number over 0. We're going to look at one-sided limits. So I'm going to look at the limit as x goes to 0 from the left of 1 over x squared and the limit as x goes to 0 from the right of 1 over x squared. And you can do it by looking at a graph. If we have the graph handy, hopefully 1 over x squared is one of those graphs that you already know what it looks like. But if you didn't know, then we will do a table of values. If you're already familiar with 1 over x squared, then we hopefully know that this is what the graph looks like. There is, I have a handout and I'll post it on Canvas of graphs you should know. So things like y equals 1 over x, y equals x squared, y equals x cubed, sine x, cosine x, tangent, inverse tangent, e to the x, natural log of x. There are some graphs that you should know from your prior math classes. So I will post that for you so that you know what graphs I'm kind of expecting you to know from your prior background in math. And then there are some that we just don't know. And in this class, we're going to learn to graph them, which is why a graphing calculator is not allowed or required. So this is what y equals 1 over x squared looks like. And so we can see that as x goes to 0 from the left, what is it approaching? So as x goes to 0 from the left of 0, notice that the y values are going towards positive infinity. And as x goes to 0 from the right, we are also going towards positive infinity. Now, if you didn't have the graph handy or you didn't remember what it looks like, we can look at a table of values, right? So from the left, you can look at, you're going to 0 from the left. So if you're to the left of 0, you're less than 0, which means you're a negative number. So you can think of like negative 0.1, negative 0.001, and see what is happening here. So when you play it in, right, it'll be 1 over negative 0.1 squared. So notice that 0.1 is 1/10, right? So then this is going to become 1 over negative 1/10 squared. Now so then the negative is going to get squared, becomes positive. So this is going to be equal to 100. And then because it's really 10 squared, so 100. And then the same thing here, you're going to have 1 over negative 0.001 squared. So 0.001 is 1 over 1,000. So then the negative becomes positive because you're squaring it. And so this value is going to be 1,000 squared. So notice that that is already a pretty huge number. So as you're getting close to 0 from the left, this is going to go towards positive infinity. So from these two, I can say that it's going to go towards positive infinity. And then try to go, we're not looking at 0 because it's not in the domain. So we're going to skip 0. And then we're going to go, okay, what about positive 0.1? And what about positive 0.001 or 0.01? And we're going to get the same values as here, right? Because the square is making the negatives positive, but when they're already positive, they're going to be positive. Anyway, so this is going to be 100 and this is going to be 100 squared. So those are going to be pretty big. So this is not in domain. And so I can tell that, okay, so both sides are going towards positive infinity. So I can say then, therefore, the limit as x goes to 0 of 1 over x squared is positive infinity, right? So now the limit is telling you what is it approaching. It's asking you what is it approaching. So it's approaching positive infinity. It's growing without bound. Is another way of saying it. It goes towards positive infinity, growing without bound. If it went to negative infinity, we will say it's decreasing without bound. So increasing without bound goes to positive infinity, decreasing without bound goes to negative infinity. So let's try the second example. So now our last example. Limit as x goes to -2 of this rational function. So same thing, plug in the value. So when you plug in -2, what do we get? -2 minus 3, so you're going to get -5 on the top over -2 plus 2, 0. So you get a number over 0. What does that mean you should do? Look at one-sided limits, because that means you likely have a vertical asymptote. Right? -2 is not in the domain of this function. So the reason that it's not in the domain is because it could be a vertical asymptote, or it could be a hole in the graph. But to have holes in the graph, we know that then the term should cancel with the term in the numerator. That does not appear to be the case here. So we look at one-sided limits. So take a look at the limit as x goes to -2 from the left of x minus 3 over x plus 2. So pick a value to the left of -2 and plug it in. We know it's either going to be, since it doesn't cancel out with anything, it's likely a vertical asymptote. So we want to see, does it go to positive infinity or negative infinity? So pick a value and plug it in. So let x equal something to the left of -2, sorry. So that means you're smaller. And for negative numbers, a number line might be helpful. So here's -1, here's -2, here's -3. So if you're to the left of 2, you're over here, right between -2 and -3. So let's pick like -2.1. And what does this become? So x minus 3 over x plus 2 will be -2.1 minus 3 over -2.1 plus 2. And we're looking for, is this going to be positive infinity or negative infinity? So that's what I'm looking for. So I'm just really looking for the sign. So notice that the sign -2.1 minus 3 is -5.1, and -2.1 plus 2 is -0.1. Negative divided by a negative is positive, and you can kind of already see here this is going to be a big number. So this then is going to go towards positive infinity. And so now let's look at, so I know I'm doing it slightly different than I did with the other one. I used a chart for the different example. So here I'm doing it more one at a time, the one-sided limits. So as x goes to -2 from the right, if you're to the right of 2, you're bigger than -2, so you're over here between -2 and -1. So you can pick like, let x be -1.9, right? So you're over here to the right of 2. You're still in the -1 point something, coming up to -2. So let x be -1.9, plug it in. So I'm going to have -1.9 minus 3 and -1.9 plus 2. So now notice here, this is going to be -4.9, but now this is going to be positive because you have -1.9 plus 2. 2 is bigger, so you're going to have 0.1. So you have a negative divided by a positive. This is going to be a negative number. So this is going to be going towards negative infinity. So it's still an odd asymptote. They go to different infinities. So we will say the limit as x goes to -2 of x minus 3 over x plus 2 does not exist. We have a vertical asymptote there, an odd asymptote. So we have an odd asymptote, vertical, at x equals -2. So odd asymptote just means they go to different infinities. Even asymptotes, they go to the same infinity. All right, email me if you have any questions.